Hi all. So today I'll be discussing about the effect of roughness in a potential on the transport coherence and stochastic resonance. So why did we choose a rough potential? So we all know that in the macroscopic scale, any sort of roughness on any surface will hinder the transport. For example, the transport on a smooth road is much easier than the transport on a road with bumps and potholes. It will slow down the speed of the vehicle. So, but however, when it comes to the microscopic scale, especially when we consider the case of a Brownian particle, the thermal fluctuations play an important role. So, the interplay of roughness and the thermal fluctuations can result in some surprising effects. So, it is important to understand such effects because in various phenomena like protein quakes and also supercooled liquids and gases, their energy landscape seems to have a hierarchical structure. Like given in the schematic image, they have multiple potential minima within one potential minima. So it is important to understand how such energy landscape will affect the transport of Brownian particle. So here we can generate such energy landscape by superimposing a fast fluctuating function onto a smooth function. So we can have two types of roughness, that is deterministic roughness and random or disordered roughness, which is analogous to the bumps and potholes on the road. So it is obvious that we will expect this rough potential to hinder the particle transport, and it has been reported that the diffusion happening in the presence of harmonic rough potential, the diffusion gets reduced. But however, recent studies reported that the particle transport can be enhanced in the presence of such rough potential when there is a time dependent force or a non-Gaussian noise. And our earlier work also reports that particle current transport, coherence and diffusion are enhanced in the presence of a rough washboard potential in a Gaussian noise. So what's new in this work? So here we will explore the transport coherence and efficiency, thermodynamic efficiency in a rough potential in the presence of a time dependent force, which has been not deeply explored. Similarly, we will also explore the stochastic resonance. So moving on to the first case, here we have considered an overdamped rocking ratchet. So the model is given here, and there is a time dependent force f of t, and this whole model is described by the Langevin equation. So the important factor is the potential V of x. It is generated by superimposing the rough potential V1 of x onto the smooth potential V0 of x. So here epsilon is the amplitude of the tiny potential well, and lambda 1 and lambda 2 are the spatial frequencies of roughness. So by tuning these two parameters, we can control the shape of the rough potential. So we will rock the potential using the time dependent force like this. And moving on to the results, here we have calculated the average velocity, effective diffusion coefficient and Peclet number. So Peclet number quantifies the transport coherence by incorporating both drift and diffusive terms of the system. So in the results, we find that at the these results shows that the average velocity is improved by the amplitude of roughness at some optimum value. So at some optimum epsilon, we find that the particle current is enhanced, and also the diffusion coefficient in that set regime is reduced, and we can see that the Peclet number is also improved by the roughness at some optimum epsilon, at the same optimum epsilon value. So in result, we can say that the transport coherence is also enhanced by the presence of roughness in the potential, and this enhancement of particle current and transport coherence is much greater when the temperature is lower. So this is because instead of hindering the particle transport, the roughness in the potential acts as a ladder, and it will prevent the backward movement of the particle. So it will aid the particle to easily cross the potential barrier, and thereby it increases the particle current, and also this results in the much more reliable or regular transport in the system. However, at very large roughness, the particle gets trapped inside the potential and it will reduce the particle current. So we have also calculated the thermodynamic efficiency of the system, and we find that the efficiency is also improved or enhanced by the roughness at some optimum epsilon and optimum spatial frequency, and we also find that this enhancement due to roughness is greater at low temperature. Now moving on to the next case where we have studied the stochastic resonance in a rough double well potential. So here we have considered an overdamped Brownian particle in a rough double well potential, and this potential is generated by superimposing the function Vr of x onto the double well potential, and we have a weak periodic signal f of t, and we are trying to find how the roughness impacts the stochastic resonance in the system. So here we have calculated the energy input of the system, which acts as a very good measure for quantity to measure the stochastic resonance, and we have calculated using the stochastic energetic formalism, and we find that energy input shows a resonance-like behavior with the amplitude of roughness and spatial frequency of the rough potential, and we find that it is improved at some optimum epsilon and spatial frequency. So here also what happens is that the roughness acts as a ladder and it will prevent the backward movement of particle. So this will aid the interval oscillation, which is very important for stochastic resonance to happen. So we can in result say that the roughness in the double well potential will improve the stochastic resonance, or it will result in a amplification of weak signal will be greater in the presence of rough potential when compared to a smooth potential. So let me quickly go through the another case. So we have considered an underdamped Brownian particle in a rough potential, and here we have considered two types of rough potential, VR1 and VR2, and in these two cases we have calculated the diffusion and particle current. So for the first case of rough potential, we observe that the diffusion is improved by the roughness, and we also note that when inertia is present in the system, as we move from the overdamped regime to underdamped regime, we observe an enhancement of diffusion, and similarly as we move from the for the overdamped case, if we move from the smooth potential to rough potential, there also we observe an enhancement of diffusion, and for the rough potential in the presence of as we move from the overdamped to underdamped regime, there is an enhancement of diffusion. So the enhancement of diffusion is much greater in the presence of inertia when compared to the overdamped regime. This is observed for the first case of potential, and for the second case of rough potential VR2 of x, we observe an enhancement of particle current at some optimum epsilon, and this is because here what happens is that the roughness, when we add roughness to the potential, when the tilting force, so there is a tilting force that tilts the potential, and if the tilting force of is less than the critical tilt of the potential, we find that the roughness reduces the total potential barrier of the system. We can see in the third figure, when we add an optimum value of roughness, the potential barrier reduces when compared to the smooth potential. So the black line is the smooth potential and the red line is an optimum value of roughness. We can see that that barrier is much lower. So it will be easier for the particle to cross that potential barrier, and as a result the particle current is enhanced in that regime. So, and however, the inertia further improves this enhancement. So we can say that, to conclude, we can say that the roughness has a constructive effect so far for the cases we have considered, and at low temperatures for the overdamped rocking ratchet, the enhanced roughness in the potential enhances the particle current and also transport coherence. Similarly, we also observed an enhancement of efficiency for the overdamped rocking ratchet due to the roughness. And we also highlight that the roughness in a double well potential can result in the improvement of stochastic resonance.
Questions?
So in these cases we have not explored that aspect, but for other cases the absolute negative mobility has been reported in the case of rough potentials when there is a time dependent force acting on rocking ratchet. Yeah.
If no, let's thank the speaker.